Statistical process control, or SPC, is a form of quality control that can be used in many types of processes. When it's used correctly, SPC can help maintain or improve the quality of a process and the quality of the product being produced. With SPC, control charts are used to provide information about whether a process is in statistical control or out of statistical control. The nature of the variation that occurs in a process determines whether the process is in statistical control or out of statistical control. There are basically two types of variation that occur in a process: normal variation and abnormal variation. When only normal variation is present in a process, the values that are plotted on an SPC control chart fall within the chart's control limits, and they fall in a random pattern. In this situation, the process is said to be in statistical control. On the other hand, when there is abnormal variation in a process, plotted values may fall outside of the control limits. These plotted points are sometimes referred to as outliers. When one or more outliers appear on a chart, the process is generally considered to be out of statistical control. Now, there are situations that don't fit cleanly into either of these two categories. For example, in some situations, abnormal variation exists in a process, but the plotted data points remain within a chart's control limits. This is often referred to as instability. That is, the process is unstable. The plotted points for an unstable process often form a recognizable non-random pattern. When a process is out of statistical control, some sort of action is usually needed to bring it back in control. The action that's taken may be as simple as making an adjustment to restore control of the process, or it may involve maintenance to the systems in the process. With SPC, the response to an out-of-control process is intended to eliminate whatever is causing the process to be out of control. The decision to make adjustments is usually based on the indication of an out-of-control situation. While control charts provide good information about whether a process is in control or out of control, no control chart can identify the problem that's causing the process to be out of control. To do that, additional information is needed. One way to help identify problems in a process is by keeping a written log of what's going on in the process. Keeping a written record of process conditions can sometimes make it easier to narrow down the cause of a problem. Then, if the control charts indicate that there's a problem in the process, the operator can refer back to the log for more specific information. The X-bar chart gets its name from this letter and symbol. The X represents the value of the variable being measured in a process. The line above the X, or the bar, is a mathematical symbol that represents an average. So the X-bar chart is used to plot the average of the values taken from the sample group that's collected from a process. An X-bar chart has an upper control limit, a lower control limit, and a process center line. On an X-bar chart, the center line is sometimes referred to as X double bar or as the overall average. The y-axis on an X-bar chart displays the average value of the samples taken from the process in the appropriate units. The x-axis displays how often samples are taken, again in the appropriate units. To see how to plot a value on an X-bar chart, we'll use temperature readings taken at 4 locations around this liquid storage tank for our sample group. Before the chart can be plotted, we have to record the readings. For this example, we'll say that the temperature readings are taken every hour. Once an hour, the temperatures at the 4 locations are taken and recorded on a data sheet. We'll say that the 4 readings are 70, 74, 73, and 75 degrees. The next step in plotting the value on the control chart is to calculate the X-bar value, that is, the average. This X-bar value is calculated like any other average. First, the readings are added together. In this case, the total of the 4 temperature readings is 292. Then the total is divided by the number of readings. 292 divided by 4 yields an X-bar value of 73. Once the X-bar value has been calculated, it can be plotted on the chart. First, find 73 on the y-axis and draw an imaginary line perpendicular to the y-axis at that point. Then find the appropriate time value on the x-axis. We'll say that the readings were taken at 2 p.m. Draw an imaginary line perpendicular to the x-axis at that point. The point at which the two lines intersect is where the x-bar value is plotted. Finally, draw a line on the chart to connect this value to the value that was plotted an hour before. The values that are plotted on an x-bar chart should fall within the upper and lower control limits. If they don't, the process is out of control. In the example we just looked at, each x-bar value represented the average of several temperatures taken at the same time. In another application, the x-bar values may be determined differently. But regardless of how each x-bar value is determined, it still represents the average of the variable being measured. This is a typical R chart. R stands for range, and an R chart indicates the range of the variable being measured. Range is basically the difference between the highest value and the lowest value in a sample group. An R chart has an upper control limit, a process center line, which is sometimes called R bar, and a lower control limit. The lower control limit on an R chart is often set at 0. That's because, in some cases, when the control limits are calculated, the lower limit comes out to be less than 0. And since there can't be a negative range in a process, the lower limit is simply set at 0. The x-axis on an R chart is used to display how often samples are taken in the appropriate units. The y-axis on an R chart is used to display the range of the sample group, again in the appropriate units. To see how to plot a value on an R chart, we'll use sample data consisting of temperature readings that were taken at 4 locations around this liquid storage tank. The recorded readings are 70, 74, 73, and 75 degrees. To find the range of these readings, we take the highest value, 75, and subtract the lowest value, 70. In this case, the range is 5. This value can then be plotted on the R chart. First, find the value of 5 on the y-axis and draw an imaginary line perpendicular to the y-axis at that point. Then find the appropriate time value on the x-axis. In this case, the readings were taken at 2 p.m. Draw an imaginary line perpendicular to the x-axis at that point. The point where the two imaginary lines intersect is the point where the range value is plotted. Finally, draw a line to connect this point to the point that was plotted when the last readings were taken. The plotted values for the range should fall within the upper and lower control limits. If they don't, there's an abnormal variation in the process. X-bar charts and R charts are ordinarily used together to monitor a process. This is because each chart provides a different type of information, and it's possible for a problem to exist in the process but show up on only one of the charts. Let's see how this can happen. We'll use process fluid flowing through a pipe for our example. We'll say that the temperature of the fluid is supposed to stay at about 50 degrees, and that 4 temperature readings are taken and recorded every 10 minutes. After the readings have been taken, the numbers are averaged, and the average value is plotted on an X-bar chart. For this process, the upper control limit has been established at 55 degrees, and the lower control limit is 45 degrees. Under normal operating conditions, all of the plotted values should fall within these limits. But suppose the next set of temperature readings looks like this. Here we see that the temperature of the fluid went back and forth between about 40 degrees and about 60 degrees. The individual temperatures are clearly higher and lower than the control limits established for the process. But when the readings are averaged, the average value is 50 degrees. And 50 degrees is right on the process center line. But when the same information is plotted on an R chart, we get a different picture. In this case, the upper control limit for the R chart is 7 degrees. But the actual range for the last set of temperature readings is 20 degrees. Since the plotted value exceeds the upper control limit for the R chart, the amount of variation in the readings is too great, and the process is out of control. What we just saw was an example of a situation in which an R chart provides better information about the process than an X-bar chart. Now let's look at another situation using different data. The range of the values in this process appears normal, since the plotted points fall below the upper control limit on this R chart. Even though the variation between the readings is small, the average of the values is too high or abnormal. In this case, the X-bar chart indicates that the process is out of control, while the corresponding R chart indicates that it's in control. Using an X-bar chart and an R chart together also makes it easier to see when too little variation is occurring in a process. For instance, let's say that all of the temperature readings taken from this process fall within a degree or two of the desired value of 50 degrees. When the average values are plotted on an X-bar chart, they fall very close to the process center line. The process appears to be in control because the plotted values are well within the control limits on the chart. On the corresponding R chart, the plotted values are close to the lower control limit. In fact, they are too close. According to the laws of probability, there's not enough variation occurring in this process. Indications of low variation should be investigated to see if a problem exists. To determine whether a low variation is abnormal, you need to understand the process and to know how much variation is normal for that process. As you can tell, when X-bar charts and R charts are used together, they provide a more complete picture of what's going on in a process. This is a typical moving X-bar chart. Moving X-bar charts are often used to monitor continuous processes. Here is the upper control limit, the lower control limit, and the process center line, which is sometimes called X double bar. A moving X-bar chart is plotted using what are known as moving averages. A moving average is calculated using the most recent sample value and a specific number of previous sample values. To see how this works, let's look at an example in which a temperature reading is taken from a process every 10 minutes. The first three readings are 65, 66, and 67 degrees. In this example, the sample group size, which is the number of recorded values used to calculate each average, is 3. When the three temperatures are added together and divided by 3, we find that the average value is 66 degrees. That value is then plotted on the moving X-bar chart. 10 minutes later, the next temperature reading is taken from the process. This reading is 66 degrees. To calculate the new X-bar value, the last three readings are used. When the last three readings are averaged, we get a new value of 66.3. That value is then plotted on the chart, and a line is drawn to connect it with the previous point. In this example, this procedure is repeated every 10 minutes. Depending on the process, the sample group size and the time interval could be different from the ones we used in our example. But the basic method of calculating the moving X-bar value is the same. The plotted value is calculated using the most recent sample and a specific number of previous samples. When values plotted on a moving X-bar chart fall outside of the control limits, the process is considered to be out of control. Because of the way a moving X-bar chart is plotted, a single sample will be used in several averagings. For that reason, a single fluctuation in a measured variable will affect several average values plotted on the chart. To see how, let's look at another example. On this chart, X1 represents the latest temperature reading, and X2 through X6 represent the 5 previous readings. In this example, a reading is taken every 10 minutes and averaged with the 5 previous readings. As each reading is taken, a new average value is plotted. In this example, a single extreme reading will affect a total of 6 plotted values, the average value that's calculated for the chart at that time, and the average values that are calculated using the next 5 readings. A single fluctuation of this sort can cause values to form a group near or beyond one of the control limits on the chart. For instance, let's say that the latest temperature reading is 58 degrees. When the new average is calculated and plotted, the point is above the chart's upper control limit. In this case, the value of 58 degrees is an extreme reading. As more points are plotted, the 58-degree reading causes the moving average value to remain near the upper control limit. Once this single extreme reading is no longer considered, its effect is no longer apparent. Since a single reading for a variable can affect several averages on the moving X-bar chart, operators should remember not to over-respond when they see an unusual plot on the chart. In some cases, a single fluctuation may not be a cause for concern. Of course, if the fluctuation causes the plotted values to exceed the control limits, the problem should be investigated. The point is, be aware that this can happen and know whether you need to take action. This is a moving R chart. It's often used in conjunction with other charts to give a more complete picture of what's happening in a process. A moving R chart has an upper control limit, a lower control limit, and a process center line, which is sometimes called R bar. With a moving R chart, each moving range value that's plotted is determined by looking at the most recent sample reading and a specified number of previous readings, and then subtracting the lowest value from the highest value. To see how to plot values using a moving R chart, let's use temperature readings taken from a process every 10 minutes. We'll be using a sample size of 3 readings to determine the values to be plotted. The first set of readings is 65, 66, and 67 degrees. To determine the moving range value for this set of readings, we take the highest number, 67, and subtract the lowest number, 65. This leaves us with a moving range value of 2. That value is then plotted on the moving R chart. 10 minutes later, the next reading is taken. It's 66 degrees. The moving R chart uses the same sample group size to plot each value. So in this case, to determine the new range value, the 3 most recent readings are used: 66, 67, and 66 degrees. Subtracting the lowest value, 66, from the highest value, 67, yields a moving range value of 1. This value is then plotted on the chart. A line is drawn to connect this point to the previous point. This procedure is repeated each time a new temperature reading is taken. That's how a moving range value is maintained for a moving R chart. Although the sample group size and the sampling interval can be different from what we used, the method of determining a moving range value is the same. As long as the values plotted on a moving R chart are within the control limits, the process is considered to be in statistical control. If values fall outside of the limits, there's a problem somewhere in the process. When you're interpreting a moving R chart, keep in mind that a single high or low reading could affect the moving range value for several more readings. It's important to take this into consideration and know how to respond accordingly. An individual X chart is plotted using single samples from the process. The actual value of each sample is plotted directly onto the chart. Individual X charts are typically used to monitor processes where single measurements are taken some time apart. For example, in this process, the pH of a liquid is checked once a day. Each day, the pH value is plotted on the chart. The points are connected to make it easier to see variation in the process. The process center line on an individual X chart is the average value around which the process should operate. If a point falls outside of the upper or lower control limit, there's an abnormal variation in the process that's causing the process to be out of statistical control. An individual X chart is often used with a moving R chart. Together, the 2 charts provide a more complete picture of what's happening in the process. The nature of the variation that occurs in a process determines whether the process is in statistical control or out of statistical control. There are basically 2 types of variation that occur in a process: normal variation and abnormal variation. When only normal variation is present in a process, the values that are plotted on an SPC control chart fall within the chart's control limits, and they fall in a random pattern. In this situation, the process is said to be in statistical control. This X-bar value is calculated like any other average. First, the readings are added together. In this case, the total of the 4 temperature readings is 292. Then the total is divided by the number of readings. 292 divided by 4 yields an X-bar value of 73. To find the range of these readings, we take the highest value, 75, and subtract the lowest value, 70. In this case, the range is 5. The X-bar chart indicates that the process is in control. But when the same information is plotted on an R chart, we get a different picture. In this case, the upper control limit for the R chart is 7 degrees. but the actual range for the last set of temperature readings is 20 degrees. Since the plotted value exceeds the upper control limit for the R chart, the amount of variation in the readings is too great and the process is out of control. A moving X-bar chart is plotted using what are known as moving averages. A moving average is calculated using the most recent sample value and a specific number of previous sample values. A moving R chart uses the same sample group size to plot each value. Here, the sample group size is 3, so the 3 most recent readings are used: 66, 67, and 66 degrees. Subtracting the lowest value, 66, from the highest value, 67, yields a moving range value of 1. An individual X chart is plotted using single samples from the process. The actual value of each sample is plotted directly onto the chart. Individual X charts are typically used to monitor processes where single measurements are taken some time apart.